Alright, calculus, so now we're going to be looking at FRQ trend. That's kind of what we're doing here. Trend number 2, which is the accumulation function and rates and how they're related to each other. So first, let's talk about kind of what you're given. You're going to be given some type of equation or some type of picture, but you're going to be given a rate, either as a graph or as a function, some type of equation. And the most common interpretation that you're going to be looking at throughout this entire thing is that the integral from A to B, or the area of a rate, is going to be equal to an accumulated total. And that's going to be a calculation that you have to do. Within that, of course, you need to do some interpretation. So that's kind of where this goes even further. So the big ideas that you're looking at beyond that is you're going to see interpretation of units, max or most of something, or the least of something, least quantity, most quantity. And then something else that kind of pops up all over the place here is that there's usually something accumulating up, increasing, but then there's something decreasing as well. So you have this overall rate is going to be equal to a couple of rates, and those two rates, it's like your input, but then from that you're going to subtract your output, the stuff that's going out. So it's kind of like a bank account. You deposit in, you got money coming in, you got money going out, and the overall, what do you have left at the end of the day? That's the in minus the out. And then occasionally, in a lot of these, you'll see kind of a wild card fourth topic in here, but the general idea is you're going to do some type of comparison. So you're going to compare with a new function, some new function, and they'll call it like g of x or h of x or something like that. All right, so let's just jump right in. No big deal. Here we go. Question number 1. So there are 700 people in line at a popular amusement park ride when the ride begins. Okay, that's not obvious as what's happening there, but that's an initial value. Initial value. Excellent. Okay, so that was given there. While there is a line, people move on. So while there is a line, so whenever there's a line, people move on to the ride at a rate of 800 people per hour. So that's a rate, and that's an output, it sounds like. The graph above shows the rate R of t at which people arrive at the ride throughout the day. Time t is measured in hours from the time the ride begins the operation. Okay, so this is a rate, people per hour. That's people arriving. This is the arrivals. Okay, how many people arrive at the ride between t equals 0 and t equals 3? So that's not saying how many people are there total or how many people go and leave. It's just how many people arrive. So part A here, we're going to jump right into it. Part A is what we're looking at is the arrivals total accumulated arrivals is going to be the integral from 0 to 3 of R of t, which we're given here, which equals this area from 0 to 3 right here. Now I'm going to look at this and I'm going to see like I have two triangles and then a bunch of boxes. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you got 14 boxes. And you might be thinking, okay, that's 14 boxes, but how many boxes, how much is in each box? Well, that's 1 unit wide by 200 units tall. So that's 14 times 200 for the boxes. Plus, I got two triangles, and so two triangles. And the triangles are each, they're actually the same, if you notice. That's kind of nice and convenient there. That's why I can multiply them by 2. But let's say I wanted to do them separate here. So each triangle is going to be 1/2 base times height. And the base for the first one is 2, the height is 200, and the base for the second one is 1, and the height is 400. And so that's our answer. Do we have to simplify? No need necessary. But I'll just write it a little bit cleaner here. 14 times 200 plus 1/2 times 2 times 100 plus 1/2 times 1 times 200, 400, pardon me, 400. There we go. Done. People is our units. Next. Part B. Is the number of people waiting in line to get on the ride increasing or decreasing? Okay, so this is interesting. The number of people waiting in line. So the total in line is going to, from t equals 2 to t equals 3, is going to equal the integral from 2 to 3 of r of t, this is the amount coming in, minus the amount coming out, which is 800 people per hour. And you might be thinking, okay, so how would I figure out if this is increasing or decreasing? Well, if I were to take the antiderivative of this, then that would give me, how much would I get here? Let's see, that would be, what am I trying to think of? So then the total weighting in line, that's a function. Let's call this the total weighting in line. We'll call that w of t equals the integral from 0 to t of r of t dt. But in general, what's really happening? What's really happening? It's going to be r of t minus 800. All right, so here we go. Now I got a better way to explain all this. It's asking you, is this amount increasing? Well, this would equal the area from 2 to 3 of r of t minus the area from 2 to 3 of 800. And if this becomes like a positive amount, if it's greater at 3 than it is at 2, then we're increasing. So how do I interpret this visually? That's, I think, what would be easiest. So let's take a picture. Let's take a look at the picture, the graph here. So here's our graph. And if I were to think, here's the people going out. It's just a constant rate. And if you notice that my rate here, r of t is greater than 800 over the interval from 2 to 3 on 2 to t equals 2 to t equals 3. Therefore, the incoming rate is greater. That's kind of like just restating the same thing. That means the overall rate of people waiting is positive. So if the rate is positive, that means the amount of people in line is increasing. Dun, 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 there we go. So because the rate is positive, that means the amount is increasing. Positive rate increasing. So that's kind of like a fundamental theorem of calculus kind of thing going on there. Relationship between the derivative and the original function. Let's take a look at the next one. At what time t is the line for the ride the longest? Okay, so the line for the line the longest, that means when is the rate of the line going to be critical? At critical. So it's the max for the line. For the integral from 0 to x of r of t minus 800. Okay, so when would that happen? Well, that could happen a couple of times. And you might be asking, okay, so how do we figure this out? Well, this right here, if we were to take the antiderivative of this, let's say that W of t, the total people in line, equals the integral, or W prime of t, that's better. W prime of t equals R of t minus 800. Then this here is going to equal R of x minus R of 0 minus, so that's our R of t, there are W of x, minus 800 from 0 to x as well. And you're trying to ask yourself, so when does that equal a max? And the idea is looking at critical points for your max will going to be where that max changes, where the rates change when the incoming and the outgoing cross each other, and also at the beginning and the end. So let's see what those values would be. So here I'm going to take this and calculate, so I'm going to actually just paste it here on the screen. Whoops, that's not what we were going for. Paste. Did we get it? Nope. There it is. Copy this. Next page. So again, we start with this like 800 thing, and notice that we have R of t, and this is the people going out, this is the people going in, and it's greater here, but then right here things change. The in is less than the out. So this is a potential max. That's a relative max. But we'd also have to figure out what is this area all the way down here. And would there be people still waiting in line? I am going to guess that this is the point at which there's the most people waiting in line, because after it, it's completely decreasing. The people in line is decreasing constantly. It hits a point here and then it's decreasing the rest of the time too. And this says how many people are in line at that time. Okay, well, because R of t is greater than 0 for 0 is less than t is less than 3, and R of t, I shouldn't say R of t is greater than 0 because it's greater than 0 the whole time, is R of t minus 800 is greater than 0, and R of t minus 800 is less than 0 for the other interval from 3 to 8, then the total is a max at t equals 3. And what is that? So we know that it happens at t equals 3. Now we just got to figure out why. Well, we figured out that the area, actually, the accumulated total in that was from part A. So let's go back and label that. Let's call this our total people, but we need to, let's call it P. We need to label it. And here's why. So this max amount of people is P from part A plus 700 more. And you're probably asking, what was that 700 from? Well, that 700 was the initial value. So I'm not even going to calculate it, but I know that that's what it would be. All right, let's see what else we got for this question. It says, at what time is P the longest? Oh, it looks like we already kind of figured that out. Did we go back? There we go. Oh, that's, I think, what we duplicated. Write, but do not solve an equation involving an integral expression of r, whose solution gives the earliest time t which there is no longer a line for the ride. Okay, so this is interesting. We know that the integral from 0 to x of r of t minus 800 equals the total people in line. Now, fortunately, we know that this actually is equal to the initial value. We'll call it like W of 0 minus W of x. And we know what this is here. We know what W of 0 is. That's 700. So we have to do the integral expression from 0 to x of r of t minus 800, which is equal to 700 minus W of x. And we could solve that. That's the really cool thing. And that's it. That's pretty much it. Whenever that equals 0, or I shouldn't even say this, whenever this does equal 0, whose solution gives the earliest time which there is no longer a line. Okay, so this is going to be equal to W0 minus W of x. So this means that W of x, let's see if we can rework this a little bit here, that our total people waiting in line is just this plus W of 0. Let's do it that way. And we want that to equal 0. So that's going to be the integral from 0 to x of r of t minus 800 dt, of course, plus 700 equals 0. There we go. When that equals 0, then we're good. When our overall area equals 0, we would find out what that answer is. That's it. That's it. Done. Does it say any justification? No. It says, there we go. All right. So let's keep going. Let's see what else we can get that are trends, similar things to this. Okay. Now notice we're not given a picture, but instead we're given an equation. So we have there's no snow on Jan's driveway from midnight to 9 a.m. So that's like from 0 to 9. Snow accumulates on the driveway, and that's piecewise function here. Oh no, that is by this. This is what's happening. That's how the snow is coming on. Where t is measured. Janet starts removing the snow at 6 a.m. T equals 6 at the rate g of t in cubic feet per hour. That's a unit worth our notice there. So right here, not removing. But then here and here, it is removing. So then we need to see how many cubic feet have accumulated. Notice they even use the word accumulated there. We'll jump right in here to the accumulation. How many cubic feet of snow have accumulated on the driveway by 6 a.m.? Remember that the integral of your rate coming in, I guess you could say, from 0 to wherever, from A to B, is going to equal to the accumulated total. So that's going to be the integral from 0 to 6. That's the first 6 hours of f of t dt. It's going to equal. Now at this point we need to warm up the calculator. So I'm going to go back here and see what that equation was that I need to type in. It was 7t times e to the cosine t. So equals the integral from 0 to 6 of 7t times e to the cosine t dt. Let's see what we get from our calculator. Trusty calculator. Oh, validating software license. It's still warming up there. So that's all we would calculate there. And I'm going to come back to that here in a second once the calculator warms up. Hopefully you guys can get that just as fast. Find the rate of change of the volume of snow on the driveway at 8 a.m. Okay, so the rate of change. This is talking about our overall rate. And at 8 a.m. Okay, that's interesting. So we got to see what's happening there. That's going to be the input minus the outputs. And in reality, that is f of t minus g of t, because those are rates. Both f and g are rates. Remember, g of t is the shoveling, while f of t was the snowfall. Okay, so that's what our rate is. It's the input minus the output. Now to simplify that, that's going to be 7t e to the cosine t minus, What's g of t? Well, at 8, it's actually something specific because it changes. So at 8, that would be the third one here. That'd be 108. 108. That's how fast it's going. Minus 108. .108. Now at this point, I do need to plug in the overall rate. I need to plug in 8. So f of 8 minus g of 8 is going to be 7 times 8 times e to the cosine of 8 minus 108. That's it. It was that easy because the overall rate is that input minus output. They're just trying to measure, can you tell that it's not about just the snow coming down on the ground, but it's the overall, the change coming in and the change going out. Let's see if our calculator's warmed up at this point. It is. So here is our screen. Let's see what we got. We're going to take the integral. First we got to type this in. 7 times the variable times e to the cosine of the variable. Close both of those off. Our window, we're looking from 0 to 12. That's fine. I'm guessing that we're going to have a lot here, though. Let's start with 0 and go up to like 400. Let's see, does that give us enough? Quick, go to. Where are we missing something? Oh, press that twice. Oh, we don't even have that much. That's 400. Maybe I'll go up to like 200. And I'm going to count by tens. 200. Count by tens. That looks quite a bit better. Okay, so the snow is coming on, and then boom, it comes way up, and then boom, it comes way up even more. So what would the area from 0 to 6 be? That's the big question. We're looking for second. Calculate the area is number 7. 0 is the left bound, 6 is the right bound. The total area is 142.74. 142.27469. Now we should put units in here. Cubic something. Cubic something. I know it's something. Cubic feet. Alright, next. We're in part C already. Let h of t represent the total amount of snow in cubic feet that Janet has removed from the driveway. So that means that h of t is the accumulated rate, or the accumulated total of output, which is going to be the integral from 0 to 9 of g of t. It's just the rate going out. So it needs to be a piecewise to function with domain 0 to t to 9. Okay, well, we got to split this at 6 and then again at 7 because g of t changes at 6 and 7, which is going to be the integral from 0 to 6 of 0 dt. That's just nothing. That's going to disappear. Plus the integral from 6 to 7 at of g of t dt, and plus the integral from 7 to 9 of g of t dt. And it's the first one's 0. This next one is actually, what was it, 108? No, 125, I think. Let's take another look at it real quick. It was 125. 125. So this one's 125. And this next one is 108. Okay, so h of t equals that. So that means h of t equals, for 0 to 6, 0. She's accumulated 0. And then from 6 to 7, she's accumulating 125 per hour because the antiderivative of 125 is just 125t. And then 108, so that actually this was like h of 9, was equal to that. That's not really what we were looking for. Then the next one would be 108t from 7 is less than t is less than 9. There we go. That's it. That was Easy. That was way easy. Let's see what else they're asking. How many cubic feet of the snow are on the driveway at 9 a.m.? Oh, that's what we have to do. How many cubic feet of snow? So the accumulated overall is going to be the integral of the input minus the output from 0 to 9. So I'm going to split this up into two integrals. For 0 to 9 of the input, because I can do that with my calculator pretty fast, minus the integral from 0 to 9 of the output, which we just started to break apart because this gets broken up into three pieces. It's going to be from 0 to 6, that's 0, so we don't really need that, plus the integral from 6 to 7 of 125, plus the integral from 7 to 9 of 108. And then this integral from 0 to 9 of f of t dt. At this point, if you think she did 125 cubic feet of snow for an hour, how much did she do from 6 to 7? That's 125. And then she did this one, 108, for 2 hours, so that's 2 times 108. And then for the original one, that's going to be a decimal approximation, which I think we did from 0 to 6, but now we've got to calculate it from 0 to 9. So I'm going to do second, calculate the area from 0 to 9. And that would give me, how much? 367. Let's see if we can get it in there. Excellent. So just, you would have it on your calculator right in front of you. So this would be 367.3346 minus this total snow at t equals 9 is this cubic feet. Do we have to justify anything? No, we did it. Check. Just a calculation. Do you have to simplify that? No, of course not. It is not necessary. Oh, that should have been a plus. There we go. Whoa, almost got that wrong. Okay, so again, the accumulation is equal to the integral of the rate, and that's generally the idea. And the overall rate is going to be your in minus your out. These two key ideas are huge. You're going to use them over and over again. Let's do them again. Let's see another couple of trends here. A cylindrical can. Radius 10 millimeters, used to measure rainfall in Stormville. The can is initially empty and rain enters the can during a 60-day period. It's 10 millimeters for the radius. The height can be modeled by the function s. S of t is in millimeters. And the rate, oh, this is a rate. Notice this. That's a rate. 2 sine of 0.03 t plus 1.5. According to the model, what is the height of the water in the can at the end of the 60-day period? Okay, so this is getting into an accumulated height. So S of 60, and does it start out at 0? Let's check that. Can is initially empty. They did have to tell us that. S of 60 minus S of 0 is going to be the integral from 0 to 60 of S prime of t dt. And that's just a fundamental theorem of calculus thing. It is very similar to like the accumulation of something over time and how it would give us a total. But let's kind of break this down. Well, we can do this with our calculator, and this is just 0. So S of 60 equals, let's see, the integral from 0 to 60 of, what's our calculation, 2 sine 0.03 t. 2 sine 0.03 t plus 1.5. Alright, so go into my calculator, y equals 2 sine 0.03 times the variable, and then plus 1.5. There we go. Now when I'm looking at my window, I know I'm going from 0 to 60. Now the height in millimeters is probably not going to go up to 200. Maybe it does. That would be quite a bit. But I'm guessing that, let's see, what are we going to do here? No, I think it's going to go up to more like 5. 0 to 5. Let's see what happens. Yep, that's pretty much what happens, and it kind of flattens out there for a second. So now I need to calculate this from 0 to 60. So second, calculate the area from 0 to 60, and I get the total area is 171. So this equals 171.81347 millimeters. Next, keep on going with the same idea. According to the model, what is the average rate of change in the height of water in the can over the 60-day period? Okay, no, so this is kind of interesting. The average rate of the height is going to be equal to S of 60 minus S of 0 over 60 minus 0. We already figured this out, so this is our answer from part A. So let's say that we labeled this S of 60. So equals the amount of water. Let's call it W. Equals W over 60. Done. That was so easy. Wait. It said what's the average rate of change in the height of water? So we're talking about the rate of change of height, which would be millimeters per, and the units that we're talking about here is day. That's it. That's it. We already figured this stuff out. We just divided it by that. And that's all you got to do. No big deal. That was super easy. Assuming no evaporation occurs. That means only input, no output. It's only coming in. There's nothing going out. At what rate is the volume of the water in the can changing at time t equals? I'm missing something there. Let's take a look. T equals what? Who knows? At t equals 7. Take that back. Take that back. Take that back. There we go. At t equals 7. That's what I'm looking for. So that's 7 days. So the volume of a cylindrical can, and this would probably be given to you, is pi r squared h. R happens to be a constant. So this is going to be pi times, this is why they gave us that piece, pi times 10 squared. The radius r equals 10 millimeters times h. So then the rate of change of the volume, dV dt, is going to be 100 pi times dH dt. And this piece here, that's S prime of t. And they told us at time t equals 7. So it's going to be 100 pi times S prime of 7, because that's the rate of change of the height at 10 days. So we just keep going, dV dt, equals 100 pi times, now we got to plug it in. It's going to be 2 sine 0.03 times 7 plus 1.5. And we got to do units. Okay, at what rate of volume? So volume in this piece is going to be millimeters cubed per day. Piece of cake. Super, super easy. Because why is it cubed? Well, it's volume, and the length that we're talking about is millimeters, and the time that we're talking about is days. Part D. During the same 60-day period, rain on Monsoon Mountain accumulates in a can identical to the one in Stormville. Okay, so it's identical. That means that R equals 100. The height of the water of the can on Monsoon Mountain is modeled by M. Okay, so this is the height. Right there. The height M of t is measured in millimeters and t is measured in days. let d of t equal m prime of t minus s prime of t. Apply the intermediate value theorem to the function d on the interval 0 to 60 is justify that there exists time at which the heights of the water in the two cans are changing at the same rate. Okay, so if d of t equals m prime of t minus s prime of t, then when d of t equals 0, that implies that m prime of t equals s prime of t. So we just got to figure out when this would equal 0. When do they equal each other? Well, let's set that up. Well, first, m of t is 1 over 400 times 3t cubed minus 30t squared plus 330t. So that means m prime of t equals 1 over 400 times the first one, if I take the derivative here, is going to be 9t squared minus 60t plus 330. All right, so we got that going on. And now all I got to do is figure out when does m prime of t equal s prime of t. Well, I got a calculator. Guess what? I can plug that in. So I'm going to go to my y equals here. And now I'm going to plug in a new function, which happens to be 1 divided by 400 times, now we got a bunch of stuff, 9 times the variable squared minus 60 times the variable. And then we got a plus 330, plus 330. Alright, let's go to our graph. Is there any time where these two functions equal each other? It's right there. You know, it's kind of hard to see, but let's do this real quick. Let's turn off the first graph, go to our graph. And then we're going to turn it back on so we can see where it is without that area calculation in there. Alright, so we're trying to figure out when these two are the same, because this one starts out slower but then increases, and this one starts out faster but then it's not going as fast later. So when do those intersect? Second, calculate intersection, which is number 5. And the first curve, we just got to get close to this thing. So we're trying to get close to that intersection. That looks good. Enter, enter, enter. And it happens at, boom. Now, we know that that's given. And you're probably wondering, well, is there an easier way to do that? There is. There is. Because it just says, use intermediate value theorem to justify that there exists a time when the heights of the two cans are changed the same. This is true here. We don't have to actually calculate it, but that is true. So to get using the intermediate value theorem, what we'd need to do is figure out where that would be. It looked like that was between 0 and, let's say, 30. That would mean that d of 0, where s of t was bigger, because the m of t was the one that went underneath it, d of 0 equals m prime of 0 minus s prime of 0, which is, this is, the second term is bigger, so that's going to be negative. And d of, let's say, 30, the first one is bigger. It's going to be m prime of 30 minus s prime of 30, which is greater than 0. Alright, so with all that in mind there, what's really happening? This means, therefore, on 0 to, oh, it's saying from 0 to 60, so change this to 60s, 60, 60, 60. Therefore, there must be a time t. There must be a time t at which d of t equals 0 by intermediate value theorem. Okay, so that's that. Intermediate value theorem says that somewhere in the middle we equal 0. Because d of t equals 0 implies this, that they're equal to each other. That wasn't too hard. It's kind of a roundabout way of using it. We could have just solved for it using the calculator, but it said apply the theorem, so we have to apply the theorem as well. Okay, let's look at the last one here, wrapping it up. Okay, we have a 12,000 liter tank of water. It's filled to capacity. It's filled to, so it's full. Time t equals 0. Water begins to drain out of the tank at a rate modeled by this. So there's our rate. And the question is R continuous? Okay, so continuity we got to look at. Then we're going to look at an average rate of change from 0 to 8. Then it's going to ask us to find R prime of 3 and say what that is. And it says, write but do not solve an equation involving an integral to find the time A when the amount of water in the tank is 900,000 liters. Okay, well, let's see what we would get then. Let's start with the first one. We're probably going to need a picture of this. There we go. Clipboard. And the first question, is it continuous? Well, for it to be continuous, that means that both sides have to be equal. So we got to figure out what's the limit as t approaches 5 from the left and see what that equals. So t as it approaches 5 from the left would equal 600 times 5 over 5 plus 3, which is really, what's that, 3,000 over 8? Alright, and then the limit as t approaches 5 from the right is going to be this bottom one, which is going to equal, and right now we're doing r of t, that should be in there, r of t, is equal to 1,000 times e to the negative 0.2 times 5 is 1, which equals 1,000 over e. And the question is, does this equal this? And I can tell you right now, no, it does not, because this e would not kind of match up with that 8. You're not going to simplify this fraction. For example, it's like, that's saying if we multiplied this by 3 over 3, that would give us 3,000 over 3e. And does 3e equal 8? Nope. It comes pretty close, but they're not equal. So is it continuous? No! The function r is not continuous at t equals 5, because the limit as t approaches 5 from the left does not equal the limit as t approaches 5 from the right. It has to be the same from the left and the right when we plug in 5. Right there and right there. And it's not. It's really close, but it's not. Next, find the average rate at which the water is draining. Okay, so keep in mind we're going to put this back in here, r of t, and I believe that this is the rate. So it's average rate of draining would be kind of like the volume at 8 hours minus the volume at 0 hours over 8 minus 0. And this right here would be the integral from 0 to 8 of the rate of r of t dt. So what we got to do then is we got to integrate from 0 to 8 r of t dt and divide that by 8 minus 0. But this on top, that's going to be equal to the integral from 0 to 5. We got to break it up into two integrals, and then from 5 to 8 of 600t over t plus 3, and then down here we got to do 1,000 e to the negative 0.2t. We got to do both of them separately and then see what we come up with. So let's do this calculator. I'm going to go to my y equals. I'm going to clear out these previous questions that we were looking at. Got some new ones going on. So the first one is 600 times the variable divided by the quantity, the variable plus 3. The next one is 1,000, and then we got e, so second, natural log, e to the negative 0.2 times the variable. Right, so I'm going to turn off y2, I'm just going to do y1 for a second, and I'm going to do that from 0 to 5. I need to go from 0 to 8, I guess you could say. And I don't know how big this is going to get. It looks like it's going to get real big, in the thousands and hundreds and stuff. So let's go all the way up to 1,000. There we go. Let's look at our graph. All right, so there's the first one. I got to do that from 0 to 5. So this, let's see what we do. Second, calculate the area 7 from 0 to 5. And that gives us 1, 2, 3, 4, 5. So that's equal to 1, 2, 3, 4.5 something 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 5073. 5073. You know, I'm going to need to definitely use some more space here, which equals 1, 2, 3, 4.5703 plus, now I got to do the other integral. Hopefully it's not too big. So now I got to go to y equals, to turn this one off, or turn this one on, turn the other one off, graph. There we go. Okay, so now we got to integrate this. So second, and calculate the area from 5 to 8, which would be 829.9146. So that's 829.9146. All over, this is 8 minus 0, by the way. He's probably wondering, so did he find that? Hey, the average rate equals this. And does it say anything about units? It doesn't, but we should indicate units of measure just in case. If we're talking about the average rate, that is, are we doing gallons? Is this measured in gallons? Let's take a look. See if we talk about gallons, liters per hour. So this is liters per hour. All right, that was part B. Let's wrap it up here. Two more parts. Find r prime of 3. So r prime of 3 is going to be the derivative. So we got 600t over t plus 3. So we got to take the derivative of this. So I shouldn't be saying that. We got to take the derivative of this and then plug in 3. Or I could just go to my calculator. Here we go. And we got to go back to my y equals. I want the first one, but not the second one. And you can actually do this. There's an advanced way to do piecewise functions, and I'm not doing that right now with logic statements and stuff. But I'm going to go ahead and calculate the slope of this. So I'll go to my graph. Second, calculate. The slope is 6 at 3. And that's about 50. And use correct units meaning. So r prime of 3 at t equals 3. Okay, so r prime of 3 equals 50. And what is this? This is liters per hour per hour. Whenever you're taking the derivative of a derivative, your time duplicates here. It's like an acceleration, kind of. Check. That was easy. Now, I have a sinking feeling that maybe we didn't have to, or we weren't allowed to use calculator with that. But I'm pretty sure that we were. Were we? Yeah, we had to be. To find the average rate of change here. Oh, man. The average rate. No, yeah, that's what we had to do. That's exactly what we had to do. All right, so let's go to part D. Those other ones we had to use a calculator for, right? But do not solve an equation involving an integral to find time A when the amount of water in the tank is 9,000 liters. Okay, so the accumulated amount equals 9,000. So how do we calculate an accumulation? That's the integral of the rate. So 9,000 equals the integral from 0 to 8 of r of t. Now, unfortunately, we have to break this up into more than one variable. So it's going to be 9, or more than one integral. 9,000 equals the integral from 0 to 5 of r of t, which I believe was 600t over 3 plus t dt, plus the integral from 5 to 8 Oh, no, wait. From 0 to 5 plus the integral from 5 to t. There we go. Or we can even call this x. What was this one? 1,000 e to the negative 0.2 t dt. So this plus this is going to equal 9,000. Now this we actually already solved, but that's just useful to know that we have to figure out what x is. Now it might be if x was less than 5, we would only need the first one. You wouldn't need the second one because you don't have to split it if you're only working in the first half of the rate. So, but that would equal what we need because the accumulation equals the integral of the rate. That's the big idea that we're seeing over and over and over again. We saw it here again. That's it. So take a look back at that, see the trends that you have. Hopefully you guys will start seeing a pattern and start to identify what the next steps would be without having to see it modeled out for you.